Hello, Algebra 1 students. Welcome to our last set of notes for Unit 5. These notes are called Difference of Squares, are on page 19 in your note guide. So today we're going to talk about kind of a special thing that occurs for when we're factoring. The essential question says, what is the factoring pattern for difference of squares? So hopefully you'll see that pattern here. We'll look at that pattern more on page 20. But first, let's just look at what this means. So difference of squares. So difference of squares are quadratic binomials. So instead of being a trinomial, it's a binomial that have perfect squares for the ax squared term and the c terms, and which are being, the key here is that they're being subtracted. So the ax is a perfect square and the c is a perfect square. It looks like this. This is the format, ax squared minus c. There is no, move this over a little bit. There is, I'll put this here, there's no bx term in these problems. It is a subtraction problem, right? It's key that has to be subtraction in order to work. And what we're going to be doing to solve these is we are going to add a 0x term to solve. So on the first page here, we're going to add a 0x term, excuse me, and solve these. And then we'll, on the second page, I'll show you a little bit of a shortcut if you want, right? So there's no bx term, excuse me, get some water. It's a subtraction problem. And we can add a add a 0x term in the middle. So let's look at how we do that. So let's go over here. So here's my problem. I have 4x squared minus 25. Now remember, if you didn't get everything written down, you can always pause the video, finish writing, and then unpause it and keep going. So here we go. We have 4x squared minus, let me pause this real quick and go cough. All right, hopefully my cough is gone. We'll see. All right, so we have 4x squared minus 25. So we are going to take this problem here and we're going to turn it into 4x squared plus 0x in the middle minus 25. Now these difference of square problems with perfect squares in the front and perfect squares at the end, we can add the 0x in here to help us do this factoring. All right, so factoring says, same rules of factoring apply here, because now we have a quadratic trinomial, right? Power 2 on the x, 3 terms. So I'm going to pull that 4 and that negative 25 and get negative 100, right? So we're going to take negative 100. Let me move this over a little bit more so we have plenty of room here. All right, so we're going to take the negative 100, and because it's negative, we need to subtract 2, and this time we're going to 0x, right? So we're going to subtract to 0. We want the end product to be 0. So if I start looking at my factor pairs, I have 1 times 100, 2 times 50, 3 does not go in, 4 times 25, 5 times 20, 6 does not go in, 7 does not go in, 8 does not go in, 9 does not go in evenly, 10 does, 10 times 10. And then we look at these, we want to subtract to a 0x. So in order to get 0, that means we're going to subtract two numbers that are the same, right? So that means when we look at our factor pairs that work, we need these guys here. We need to have opposite signs because we're subtracting, right? And so 10 minus 10 is 0. So I'm going to take 4x squared here minus 10x plus 10x minus 25, right? And then draw my wall down my two binomials. Right, so there's my wall. Now I'm going to do the factoring. So my first set of factoring here, we have 4 and 10. So 2 can come out of both of those, and an x. So I take 2x out, times 4 divided by 2 is 2, x squared divided by x is x, negative 10 divided by 2 is a negative 5. So I have 2x times 2x minus 5. And then over on the right side, I have 10x minus 25. So 10 and 25 have in common 5. So we're going to divide 5 out. So 10 divided by 5 is 2 times x. Negative 25 divided by 5 is a negative 5, right? These two things need to be exactly the same. They are. We're in good shape. So my answer is 2x minus 5 times, right? These guys are the ones out front, 2x plus 5. Right? So it does, in fact, factor. So these difference of squares do, in fact, factor out nice and clean. Okay, so let's look at number 2 here. So we're going to do the same thing here with number 2. Right, so I have x squared minus 144, right? So we're going to take and make this x squared plus plus 0x minus 144. Right, and if we're going to factor this guy, I'm going to take the 0x term in the middle. I'm going to grab, this is a 1 out front, so 1 times negative 144 is negative, looks like a negative 144. Right, we're going to try to split that apart. So I'm going to move this over a little bit here so we can see what we're doing. All right, so I have negative 144. Because it's negative, we are subtracting. And we're going to subtract to 0x, right? So again, we're subtracting to 0x. All these problems are going to subtract to 0x because 0x is our bx term in the middle. So 144, let's do our factor pairs. 1 times 144, 2 times 72, 3 times 48, 4 times 36, 5 does not go in, 6 times 24, 7 does not go in, 8 does not divide in, 9 does not divide in, 10 does not divide in, 11 does not divide in, but 12 does. 12 times 12. Some of you might be starting to see the pattern here a little bit, right? We need to subtract to 0. So these guys here, right? 12 minus 12 is 0. So I'm going to take my x squared, or my 1x squared if you want to put the 1 out front. I have minus 12x plus 12x minus 144. Right, so there I've got my two factor pairs. We're going to continue factoring. I can divide out of this guy. 12 and 1 only have a 1 in common. X squared and x have an x. You can take a 1x out, or just x if you prefer. I don't care which way you write it. X squared divided by x is x, or 1 divided by 1 is 1. X squared divided by x is x. Negative 12 divided by 1 is negative 12. X divided by x is 1. Over here, 12 and 144, my GCF is 12. Take a 12 out. 12 divided by 12 is 1 times that x. Negative 144 divided by 12 is negative 12, right? These two are the same. So I have x minus 12, or 1x minus 12. If you want to keep the 1, your choice. And then I have x and a positive 12, x plus 12. And you might remember from quadratic trinomial, we could have went straight from here to there if we wanted to, because that a term was a 1, right? If that a term, that first term is a 1, we don't have to do the whole quadratic trinomial differences of square factoring. We can go straight from the answer to the binomials. Doesn't matter, we don't have to, but we can, right? So there's my answer, x minus 12 times x plus 12. All right, now I want to, ooh, look at that, kind of went down into this problem. All right, now let's look at number 3. Now, number 3, if we're looking at it in the same fashion here, right, that we're saying, okay, it doesn't have a b term, let's put a b term in. So let's go ahead and put a b term in and see what happens. So if I do x squared plus 0x plus 36, and we try to factor it, right? So I'm going to draw in box the 0x, grab the 1, that's a 1 out front again, and a plus 36, right? So that's what we're going to use. So we need a plus 36. If it's addition, that means we need to add to 0x. This time we're adding to 0x and not subtracting. So 1 times 36, 2 times 18, 3 times 12, 4 times 9, 5 does not go in, 6 times 6. All right, so we have a 6 times 6 here, kind of looking at our pattern, but we need to add. So if I add 1 plus 36, that gives me 37. If I add 2 plus 18, that gives me 20. If I add 3 plus 12, that's 15. Add 4 plus 9, that's 13. Add 6 plus 6, that's 12, right? None of these work, right? None of these work. And none of these work because this needs to be subtraction, right? This is a very special case. We call it difference of squares. The difference part is a subtraction. If it is not, that does not like need, sorry. So it needs to be subtraction is what it says. Sorry, still haven't got my Apple pencil fixed. So, so this needs to be subtraction. If it's not subtraction, then you cannot add a 0x and factor it. Won't work. Every time you can try it, and then you're just going to end up with no factor pairs that work. And if we have no factor pairs that work, remember our answer is prime. So when you're asked to factor it, we would just say it's prime. It cannot be factored. The x squared plus 36 it can't be factored. So we do not have a factored answer. Okay, so that needs to be a minus sign in the middle. If there's no minus sign in the middle, you don't even need to try it. If you check for your GCF, right? We should always be checking for your GCF first. I have not been doing that. This is Kim's bad. I made these problems, they don't. First 3 problems did not have a GCF, but check for that GCF first, and then if there's no GCF, if there's not a minus sign between those 2 perfect squares, then you're done. You cannot factor further. All right, so now we're gonna go look at another one on the next page. So let's see. So let's go to page 20, right? Page 20 here. And I'm going to zoom up here, 9x squared minus 25. Up here at the top, right? So if we were, let's just do this problem like we were doing on the other side, right? So we're going to start here, and we're going to rewrite this problem. So I have 9x squared plus 0x minus 25, right? And then we're going to box the middle term. I'm going to pull the left and the right. So 9 times 25 is negative. So negative 225, right? That's negative 225. If you can't read my writing so well, I'm going to move this over a little bit. All right, so negative 225 means we're going to subtract 2, again, going to 0x. All right, and so if we start looking at factor pairs, I have 1 times 225. 2 does not go in evenly, but 3 does. 3 times 75. 4 does not go in, but 5 does. 5 times 7, not 75. Whoops, 5 times 45. 6 does not go in. 7 does not go in. 8 does not go in, but 9 does. 9 times 25. Oops, why did I put 2 dots? 9 times 25. There we go. 10 does not go in evenly. 11 does not. 12 does not. 13 does not. 14 does not. But the number 15 does. 15 times 15. Hopefully you were kind of looking for this, right? We need to subtract to 0. We need to find where they have that same number, opposite signs, right? So if I was going to then subtract this, I have 9x squared minus 15x plus 15x minus 25, right? To finding my GCF here, right? I can divide out of the first and the second one a 3x. So 3x comes out. 9 divided by 3 is 3. X squared divided by x is x. 15 divided by 3 is 5. There we go. 15 and 25 have a GCF of 5, right? So 5 comes out front. 15 divided by 5 is 3 times that x. Negative 25 divided by 5 is a negative 5. Oh, why do I have a plus sign there? There was a minus sign. There was a minus sign here, right? So this should be a minus 5. Oh, Miss Kim. All right, so we should have 3x minus 5 and 3x minus 5. Again, check your work. It's so easy to make mistakes. I don't have you guys in class correcting me as I work. I apologize, right? Because negative 15 divided by 3 is a negative 5. So we should have 3x minus 5 on the left and 3x minus 5 on the right. And then we're going to put this 3x and this 5 together. So we have 3x plus 5 times 3x minus 5. Doesn't matter which order you put them in. There's my answer. Now, I'm going to show you a shortcut that works for these quadratic trinomials, right? So because these are quadratic trinomials, we can do this because it's called not quadratic trinomials, because these are difference of squares, and we turned them into a quadratic trinomial, right? The 0x in the middle, but this is a difference of squares. And what that means here is if I took the square root of 9x squared and I took the square root of 25, right? So the square root of 9x squared, right? If we did 3 times x, remember last unit with the simplifying radicals, why we did that, right? This becomes 3x. The radical goes away because everything came out from underneath. The square root of 25 is the same as the square root of 5 times 5. Square root of 5 times 5 is 5. So these difference, here, remember this is a difference of perfect squares. These are 2 perfect squares. 9x squared is a perfect, take the square root of it, it's 3x, right? 3x times 3x is 9x squared. And then 25, square root of 25, square root is 5, right? 5 times 5 is 25. They're perfect squares. We can take these now and we can write our answer. If you notice the pattern, right? This is 3x plus 5 times 3x minus 5, because one is always going to be plus and one is always going to be minus on these problems, right? So these are the same thing. If you notice here, these are the exact same answers. 3x plus 5 and 3x minus 5 are the binomials. So if it is a is a binomial that is perfect squares, right? It's a subtraction sign in the middle, and it's a perfect square in the first term and a perfect square in the second term, and it's a quadratic, right? These are still quadratics. Then you can take the square root of the first one, the square root of the second one, and you're going to get to these answers. You can do this method over here. You can just add the 0x in and keep factoring every time. It will totally work. It'll totally tell you if it's not factorable. But if you notice it is a difference of squares, it's one of those things when you get into pre-calc, or if you go up into higher math, you're going to want to start recognizing these difference of perfect squares. Because when we factor things, we often have a difference of squares that we need to factor out after we start doing some work. So these show up a lot. So this is why we show it, and we want to expose you to it. Okay? All right. We got 2 more problems to look at. Now, number 5 down here. First rule of factoring is to make sure it's in standard form. So this has an x squared term and x, right? So we're in standard form. Second rule of factoring, always, and I probably should have been saying this all along, is to check to see if we have a GCF. Now I look at 3x squared and I look at 12x and I say, okay, they both have an x, right? So we can take the x out of both terms, and 3 and 12 can both be divided by 3, right? They have a GCF of 3x. So I'm going to divide both of these terms by 3x. Right? So we always start with the GCFs. Always start with GCF. Start with GCF if there is one. If there's not one, obviously just go to the next step. But if there is one, take it out. And so when I take it out, I have 3x out here. 3 divided by 3 is 1. X squared divided by x is x. And then negative 12 divided by 3 is negative 4. X divided by x is 1. Now I look at this problem. I have 3x times x minus 4. There is no quadratic, right? This is not a quadratic. It is a difference, and they're both actually perfect squares, right? Square root of 1 is 1, square root of 4 is 2, but it's not a quadratic. If it's not a quadratic, we are done, right? We're looking for these. This is my answer. 3x times x minus 4. That's it. We have nothing else to do. So sometimes all you have to do is take out a GCF, and there's nothing else to be factored. That's why we always check for those GCFs first. There's no other way to factor this. We can't add a 0c. The only time we can add extras into our binomials is put a 0x in the middle if we want to test that. But we would never add a 0 as a c at the end. It would not make any sense. We would just take out the GCF because they both would have a variable, and then we would be done. Okay? All right. One last problem. Number 6. So coming down here to number 6. So if we go back to this idea from number 5, we said, okay, first thing we check is if it's in standard form, it is. Second thing we check is it has a GCF? Well, this one does. They're both even, so I'm going to take a 2 out, right? I'm going to take 2 out. I have 2 times 16 divided by 2 is 8 times x squared minus 100 divided by 2 is 50. And then I look at this and say, oh, okay, wait, I didn't take out enough because 8 and 50 both can also take out another 2. So, right, so take that other 2 out. So 2 times 2 is 4 out front. 8 divided by 2 is 4. X squared minus 50 divided by 2 is 25, right? So now I took out a GCF. I took out a GCF of 4. I look at what's inside. 4x squared minus 25. I see a minus sign in the middle. So it's a difference. It's a difference problem. Then we can check to see if it's a perfect square, or you can add a 0x and go. I'm going to check to see if it's a perfect square. So I have the square root of 4x squared, right, which is the square root of 2 times x, which means it's the 2x, right? I could take a group of 2 out, and I could take the x's out. That is a perfect square. And then I'm going to check 25, right? Square root of 5 times 5, there should be an equal sign, which is 5. This was actually our first problem too, I believe, 4x squared minus 25, if you recognize it from number 1. Right, so 2x and 5, they're both perfect squares, and there's a different sign, right? There's a minus sign here in the middle. So that means this final answer, don't forget, here, I'm going to circle it in red here, don't forget that GCF you took out front, right? The final answer is 4 times 2x plus 5 times 2x minus 5. Now, if you didn't like that shortcut that I just did, then you can feel free to rewrite it 4x squared plus 0x minus 25, just like we did in number 1. You already have all the work in number 1 on page 19, so look back to number 19. You could do all that work and get to that same answer, right? We already factored that, so I'm not going to factor that again. All right, so that is the answer, and that's where we want to be. Now, I'm going to box this off real quick, and I'm going to show you, let's say you looked at this problem, and you said, okay, Mrs. Kim, 16 is a perfect square, right? 4 times 4. 100 is a perfect square, right? 10 times 10. So, right, so I'm gonna go straight here. I'm gonna say Miss Kim is a different sign, the perfect squares. So square root of 16x squared is the same if you went down to prime factorization. You could have went all the way to 2's if you wanted to, right? Right? Check out these two groups of 2 and this x, or 2 times 2 or 4, 4 times 4 is 16, however you want to get there. But if you did this first and you said, okay, Mrs. Kim, this is 4x. Square root of 16x squared, square root of 16 is 4, square root of x squared is x, 4x. Awesome. And then you did the square root of 100, right? Which is really just the square root of 10 times 10. It's a perfect square. Square root of 100 is 10. So then you say, okay, well, then Mrs. Kim, this is my answer, 4x plus 10 times 4x minus 10. Doesn't matter what you put first. Right? And you say, okay, there, I'm done, right? Perfect squares. I factored it. It was easy. It's fast. I didn't even have to do all that extra factoring stuff because it was a difference problem, right? There's a minus sign here in the middle. They were both perfect squares. But remember, on the last set of notes, we talked about once you get your answer, always check to make sure, did you have any GCFs that you missed? And if I look here, I'd say 4x and 10. Oops, I can take a 2 out, right? So we have 2 times 4 divided by 2 is 2 times x. 10 divided by 2 is 5, right? That can simplify to 2 times 2x plus 5. And then times, here again, we can take out another 2. So times 2 times 4 divided by 2 is 2x. 10 divided by 2 is 5, right? So now I have 2 times 2x plus 5 times 2 times 2x minus 5, which you multiply those 2 times 2 together, that gives you that 4. And then I have 2x plus 5. Let me see if I can move this over a little bit more space. Here we go. And then we have 2x minus 5, right? And then we get to, why did it move that? Sometimes it just moves it on its own. Don't know why. These guys are the same. So if you forget to take out a GCF first, if it's factorable, it's still going to be factorable. You just use bigger numbers. But at the end, you have to check to make sure that your final answer has no GCFs left to be factored out. So you could have factored the GCFs out first, and you got to this answer over here, or you could have factored the GCFs out at the end and got to that answer over there, right? Either way will get you to the final answer in the same place. All right, so that is difference of squares. Difference of squares, they're perfect squares in the ax squared term, a perfect square in the c, and there's a minus sign in the middle. Then we can add that 0x in. We can add the 0x in all the time, and you can just check it. And then if it's not factorable, it's just prime, right? Then it's not a factorable problem. Difference of squares, if it's a perfect square in the front and a perfect square at the end, it'll always be factorable. It's always going to be a factorable problem as long as there's a minus sign in the middle. Awesome, that is the last of our notes for Unit 5. Yay, now we're just gonna have to be doing lots of practice on factoring. We'll see how you guys are, how you guys did on your multiplying quiz. I haven't looked at those yet from this last week. We'll be doing a factoring quiz this week, and then we're gonna be doing lots of just here a bunch of random polynomials. Let's try to factor them. So that's where we're headed. But you have all of the notes now for the unit. All right, we'll see you in class on Wednesday.